In the last lecture, we have started with the interpolation, and we have seen the formula for the Newton's forward difference and forward difference and backward difference also. So in the last lecture, we have seen how to find or how to write the difference table. What is the forward difference? What is the backward difference? And again, we have used the Newton's forward difference formula to find the approximate value using interpolation. Okay, so let us try to find some more examples. Let's try to go for some more examples. So I hope you are able to see this.
Yes, sir.
Okay, that's great. Okay, so we go with another example. Find the value of velocity at 25 seconds when a rocket is launched. And the following data is recorded. So we have the data recorded, and then we have to find the velocity at 25 seconds. So we have the time in seconds and velocity in kilometer per hour. Okay. Or we say this is the velocity kilometer per second. So we are having a rocket launched here, and the data is like this. We have 0, 10, 20, 30, 40, 60. Okay. So these are the seconds, and then velocity we have 0, 15, 25, 35, 70. Okay, so you got this data. Have you got this data?
Yes, sir.
Okay, so what is the example given to us? See, a rocket is launched, and then its velocity is recorded in the interval of 10 seconds. Okay, and then we want to know what was the velocity at 25th second. Okay, so we have to find this velocity using Newton's formula. Okay, so we can go find the velocity using Newton's formula. Okay. Now let us try to find. Okay, so we go with the solution. Right, V be the velocity of rocket at time t. Okay, so consider the following difference table. Okay, so we have the following difference table. You know how to construct the difference table. Okay, so we have time t and velocity v, and it is given 0, 10, 20, 30, and 6. So this much data is available with us. Okay. What is the data given? So we can see the given data 0, 15, 25. We have here 0, 15, 25, 35, 15, 70, 35, 50, 70, and 100. Okay, so we have to consider the difference for velocity. So here x is going to be t, our independent variable is t, and the dependent variable y is here v. Okay, so this is our independent variable and this is the dependent variable. So we consider the first difference, delta v. So we have, this is 15, this is going to be 10, this is 10, okay, and then this will be 15. So I hope you are able to understand the differences now. So is there any doubt in difference?
No, sir. No, sir.
No,
Okay.
sir.
You are getting this difference, no?
Yes, sir.
Okay, so this is 20 and this is going to be 30. Now we consider the second order difference. Okay, so delta square v. What is the difference here?
-5.
Good. So it is going to be -5. What is the difference here? This
0.
is 0. This is 5. Okay, here again it is 5. Here again we get 10. Okay, so this is the second order difference. Now we consider the third order difference. So we have delta cube v. So this will be 5. Is that okay? This is going to be 5.
Yes, sir.
Are you getting this?
Yes, sir.
sir.
Yes, sir. Good. This is going to be 5. This is 0. Okay. So what this difference will be here?
5.
5. Good. Okay. Now we have to consider the next difference. So delta raised to 4 v. So here we get 0. Here we have -5. Here we have 5. Next difference delta raised to 5 V. So here we get, what is the difference? Is it minus 5?
Yes, sir.
And this is going to be 10. Okay, so delta raised to 6. What is the difference you'll be having here?
15.
15, right? Okay, so this is the difference table that we have. Okay, so we have constructed the difference table now. Okay, and now we have to consider the Newton's forward difference formula. So let us try to construct the Newton's forward difference formula and the term which are important. So what are the forward differences we have to consider? These are the values for the forward difference that we have to use in formula. Okay. So these are the forward differences. Okay. And we can see these are the backward differences. Okay. But we are not going to use backward. We are going to use the forward difference. Okay. So what is the formula we have? We have Newton's forward difference formula as, so here we are having V of t. Okay, so I'll write the formula in y, and then you can understand how to relate it. Okay, so we have y at x is equal to, what we know y at x is equal to, so we know forward difference y0 plus, what we know here,
P times delta y naught.
p times delta y0, correct? Then we have p into p minus 1 by 2 factorial and delta square y0 and so on the term. Okay, what we know? We know x is equal to x0 plus ph. Okay, that's what the formula is. So here we are considering v is equal to, so we have to convert this formula in terms of v and t now. Okay, so what we know here, this is going to be v0. Okay, plus p times delta v0 plus p into p minus 1 by 2 factorial delta square v0 plus p into p minus 1 p minus 2 upon p factorial delta cube v0 and so on the terms. So here always we start with t0. So this is t0. This is corresponding. This value is v0. And this is t1, t2, t3, t4, t5. Okay. And this is going to be t6. Now here, this is v0. This value is delta v0. This value is delta square v0. This value is delta cube v0. This value is delta raised to 4 v0. This value is delta raised to 5 v0. And this value is delta raised to 6 v0. Okay, so we have these forward differences. Now, what is the value of t? So we have here where what I have now, t is equal to t0 plus th. Okay, here h is equal to, what is this time is equally spaced. So what is the step size here?
10.
10. Okay, so h is going to be 10 seconds. Okay, so h is going to be 10 seconds. What is the value of t here? So t is going to be 25. t0 is equal to 0. And h we know it is going to be 10 seconds. Okay, so can we calculate the value of E. So can we write here? This is going to be 25. This is equal to 0 plus 10 times P. So can we have 10 times P is equal to 25? So can we write P is equal to 2.5? Are you getting the value of P?
Yes, sir.
Yes, sir.
Okay. So this way we got the value of P. Now let us write down the value of P and these values of V0 and the forward differences of V0 in this formula. Okay, so let this formula 1. Okay, we call this as equation 1. Okay, so now we can write from equation 1. We have, okay, so what we'll be having here? V is equal to, okay. So V is equal to, what is V0? V0 is 0 plus,
Sir, can you please scroll up a little?
yes, okay. So here P is going to be 2.5 and here we can see V0 is 0, delta V0 is 15. Okay, so what is the next term we'll have here? So next term will be here, this is delta V0. So delta V0 is 15. Okay, plus what we have? P, so 2.5, P minus 1. So 2.5 minus 1 by 2 factorial. So 2 factorial. And here, this term is going to be delta square. Okay, so delta square is going to be minus 5. Okay, so better write, I'll write this step here. So V is equal to 0 plus 2.5 times 15 plus 2.5 into 2.5 minus 1 by 2 factorial, and this is going to be minus 5. So this is 2.5 minus 1, 0.5 minus 2 by 3 factorial. Okay, and here we have to consider delta cube. So it is going to be 5. Okay, so we got here, this is going to be 5. Now we can have plus. So it is 2.5, 2.5 minus 1, 2.5 minus 2, and 2.5 minus 3. Okay, by 4 factorial. And here we want delta raised to 4. So delta raised to 4 is going to be 0. Delta raised to 4 be 0. Okay, so this term is going to be 0 plus we have 2.5, 2.5 minus 1, 0.5 minus 2, 0.5 minus 3, and 2.5 minus 4. And here we have by 5 factorial. And we want delta raised to 5. So it is minus 5. So this term is going to be into minus 5. Please be careful for the sign and all the terms. So we have the next term. What you'll be having? 2.5, 0.5 minus 1, 0.5 minus 2, 0.5 minus 3, 2.5 minus 4, 0.5 minus 5. And here we have, this is by 6 factorial, and this is what you'll be having, 15. So next difference we have is 15. Now, this is the expression that we have got. And so we have here, this is velocity at 25 seconds. Okay. Now we have, this is 2.5 into 15. Okay. So 2.5 into 15 plus this term, what we'll be having here, this is 2.5 into 1.5 into minus 5 by 2 plus. Now see this term, what we have here. So this is 0.5 into 1.5 into 0.5. I am simplifying this expression. So 2.5 minus 1 is going to be 1.5. 2.5 minus 2 is going to be 0.5. And this is 5. And this divided by 3 factorial. So it is going to be 6. Okay. Now here we have 0. So this term will be 0. So we have to consider this term. What this term will be? So plus here we have 2.5 into 1.5 and this is going to be 0.5. This is minus 0.5 and this is minus 1.5 into minus 5 upon this is going to be 5 factorial. So that's going to be 120. Is that correct? Is that okay?
Yes, sir.
Okay. So now this term, so this will be 2.5, 1.5, going to be 0.5. This is minus 0.5, minus 1.5, and this is minus 2.5 into 50. Okay. And this term divided by 720. So this is the expression that we have. Now, if we simplify this, velocity at 25th second is equal to. So find out the value for this one. I want you to calculate this value quickly.
$29.55.
Others, please verify this value.
Sir, I'm getting 29.70.
29 point. Okay, we'll see. 29.55 is one of the answer. 29.70. Are you getting 70?
Yes, sir, 70.
Okay.
So
Any
can you
other
please
value?
scroll up a little?
Sir, I'm getting 29.55.
This expression I have written in the next step. Next page. So what is the, how many of you are reading which value?
First one.
First one.
29.55.
29.55.
Yes, sir.
So actually what we are calculating the velocity. So the velocity of rocket at 25 seconds was,
Sir, I did not actually got what is the value of P and H here.
yeah, here I have explained it, no? So what we have to consider is, see, this is the formula what we have seen. Okay, so here instead of x, we have t as the independent variable, and our dependent variable y is actually v here. So velocity is dependent on time. Okay. So the formula as x equal to x0 plus ph. So here it will become t is equal to t0 plus ph. And we have to find the value of the velocity. See, we have the question, find the value of the velocity at 25 seconds. So we have to find out v at t is equal to 25. So we have considered 25 here. And then h, what is h actually? H is the difference between x size. So what do we know? H is equal to, see, we have the formula h is equal to xi plus 1 minus xi when the data is equally spaced. Okay, so here this data is equally spaced. So data is recorded, the velocity is recorded after every 10 seconds. That's why h is going to be 10. So using the value of h and t, we have calculated the value of t, and that comes to be 2.5. Got it?
Yes, sir. Got it. Thank you, sir.
Okay, yes. Okay. So here we got actually the velocity of rocket at 25 seconds was 29.55 kilometers per second. Okay, so that was the velocity. Okay, is there any doubt in this example? Is there any doubt in this example?
No, sir.
All of you got this example?
Yes, sir.
Okay. Okay, so we'll go for the another example now. Okay. Find the value of y at x is equal to 7 using following data. So here we have x and y. Okay. By trans backward difference formula. Okay, so here we are asked to use the backward difference formula. Okay, so previous examples we have solved using the forward difference formula. Now here we'll use the backward difference formula. Okay, so let us consider the difference table for the given data. Okay. So what we have is X and Y. We have first difference, second difference, third difference, fourth difference, fifth difference. So we have x0, that's going to be 0, y0 is 2, we have x1, it's going to be 4, 6, so it is 5, 8, and 12. These are the corresponding entries. We'll continue this table here. Of 8, 10. Okay, so what are the corresponding entries? 14 and 17. Now let's have the differences. Delta square y, delta cube y, delta raised to 4y, delta raised to 5y, delta raised to 6y. These are y means y0 we are considering. We are considering the forward difference. You know the table for the forward difference and backward difference is going to be same. Okay. So here what will be the difference? This is going to be 3. This is 3. This is 4. It's going to be 2. And this is 3. This is 0 here, 1 here, minus 2, 1. It's going to be 1. This is minus 3. And this difference is going to be 3. This is minus 4. Difference is going to be 6. And this is 10. Is that okay?
Yes, sir.
All of you are getting this difference table?
Yes, sir. Yes, sir.
Okay.
Yes, sir.
Because once you understand the difference table, then it will become easy to understand the formula. So now we are supposed to use the backward differences. Okay. So what are the backward differences we have here? So we have to use xn if we are using backward difference. So these are the backward differences. So when we consider from y0, these are the forward differences. When we consider for yn, then these are the backward differences. Okay, so these backward differences we are supposed to use. Okay, so what is the formula we have for backward difference? Okay, so we have Newton's backward difference formula as. So we have y at x is equal to yn plus p times, we are using backward difference, so del yn plus p into p plus 1 by 2 factorial L square yn plus p into p plus 1, p plus 2, pi 3 factorial, and del cube yn, and plus 1 that are. Okay, where x is equal to, we know here, xn plus ph. So here h is equal to, what is the value of h here?
2.
2. Okay, so h is going to be 2. What is the value of x?
7.
X is going to be 7. So this is given in the question. Okay, so x is 7. What is xn? Xn is 10, no?
Yes, sir.
Okay, so what we have here, 7 is equal to 10 plus 2p. So can we have this? If I simplify, what we'll get is p is equal to minus 3 by 2. Is that okay?
Yes, sir.
Or we can write p is equal to minus 1.5. Okay. So minus 1.5 will be easy for our calculations. As we would write here, p plus 1, p plus 2 onwards. Okay. So this better to go with the decimal fractions rather than the simple fraction. Okay. So now we know the value of x, we know the value of p, we know all the backward differences. So here we have all the backward differences. Okay, so this is yn, this is del yn, this is del square yn, this is del cube yn, this is del raised to 4 yn, and this is del raised to 5 yn. Okay, so in the same table, you will find the forward differences as well as the backward differences. Only thing is that where is the forward difference and where is the backward difference that you have to consider. Okay, so if we consider these values, then these are the forward differences, but we have to use the backward difference. So these are the backward differences. So forward differences are at the top and the backward differences are at the bottom. Okay, so now we have these values, we have the formula. So let us calculate the value at this x is equal to 7. So we have y is equal to, this is going to be yn. So what is yn? It's going to be 17. So this is 17 plus, so it is going to be minus 1.5. And here we have, this is del yn. So del yn is 3. So we have 3 plus. So this is minus 1.5 minus 1.5 plus 1 by 2 factorial. And here del square yn. So it is going to be 1. Okay, so del square yn is going to be 1 plus minus 1.5 minus 1.5 plus 1 minus 1.5 plus 2 by 3 factorial. And here we have, this is del cube yn. So del cube yn is going to be 3. Plus we have minus 1.5 minus 1.5 plus 1 minus 1.5 plus 2 minus 1.5 plus 3 by 4 factorial. And here we have this del raised to 4, which is 6. So we got here 6. Okay. Plus we have minus 1.5 minus 1.5 minus 1. Here we have plus 1 minus 1.5 plus 2 minus 1.5 plus 3 minus 1.5 plus 4 by 5 factorial. And here we have this is going to be 10. So is that okay? Is there any more value? So we have 10 is the last difference, no? So we don't have any more value. So we don't have any more term here. Now simplify. This is y is equal to. Okay, so we got here this is 17 minus. So is that 4.5? Okay, so here what do we have? This will be minus and this will be minus. I'll write it. So this is minus 1.5. This is minus 0.5 into 1 by 2 factorial. So it is going to be 2 plus. So this is minus 1.5. This is minus 0.5. And here this term is going to be 0.5 into 3 by 6. Okay, plus we have minus 1.5 minus 0.5. Here we get 0.5 and here we have 1.5. And this term divided by 24. So here we have 6. Okay. Now we have plus. So this is minus 1.5 minus 0.5. This is going to be 0.5, 1.5, and this is 2.5 into 10. On this 5 factorial is going to be 120. So here we get the value of y at 7. So can you please tell me what is the value? Please calculate this value.
Sir, 13.32. Yes, sir. 13.32.
What you are getting?
13.32.
13.32. What about the others?
Same, sir.
Are you getting the same?
Yes, sir.
Once you confirm, then I'll write
sir.
it as a final value.
13.32.
Okay. So I hope all of you are getting the same value now. All of you are getting the same value.
Yes, sir.
Okay, that's great. So those who have not got it, the value, please check your value. If you are getting the same, then it's correct.
Sir, I am also getting the same value.
You are getting the same value or the different one?
Same, sir.
Same. All of you are getting the same value. That means this value is correct. So is there any doubt in this example? All of you got the construction of table and the solution.
Yes, sir.
Is there any
Yes, sir.
doubt?
No, sir.
No, sir.
Okay, that's good. So we have seen in the last example how to use the backward difference formula. So let us see one more example. So let's go for the next example. So we go for the example using Newton's backward difference formula. Find the value of y at x is equal to 8, where the data, the given data. Is as so we have been given the data. So this is the given data. So using this given data, we have to find the value of y at x is equal to 8. So we go with the solution. Consider the Newton's backward difference formula as. So what is the Newton's backward difference formula we have? Y is equal to yn plus p del yn plus p into e plus 1 by 2 factorial L square yn and so on. Where x is equal to xn plus ph. Okay. So here we have x is equal to 8, xn is equal to 10, h is equal to, what is the value of h here? Can you identify
Three.
h?
3.
H is going to be 3, right? Okay, so here h is going to be 3. So what we get here, this is 8 is equal to 10 plus ph. So what we can have p here. So is p is equal to minus 2 by 3. Are you getting this? So we are using 2-digit accuracy. So we are having this 66, or we can write this as 666. Better accuracy. Okay. Are you getting this value? Okay. So consider the following difference table. Okay. So what we have here, we have x, y. So it is 1. Then we have 4. We have 7. And we have 10. Here it is. This is 65. This is 343, and we have 1001. Okay. So we consider the first difference. Okay, so what is the first difference here? Is it 63? What is the difference here? Calculate this difference.
278.
278.
78. What this difference is?
658.
658. Okay. And we have to consider the second order difference. What is this difference? $115.
380.
This is 380.
Yes.
We have the third order difference. What this difference is going to be?
165.
165. That's good. Okay, so here we have to use backward difference formula. And hence, what are the backward differences we have? Okay, so this is yn, this is del yn, this is del square yn, and this is going to be del cube yn. Okay, so we have this backward differences. Now we know the formula that we have. So we have this formula, and hence we are able to find the value of y at x is equal to 8. Okay. So from above table, we have y at 8 is equal to yn. Okay. So yn is going to be 1001 plus p. So p is going to be minus. This is going to be 0.666. Okay. So here we have 0.666 and del yn. So it is 658 plus we have 0.666 into this minus minus 0.666 plus 1 by 2 factorial. And here we have, this is 380. Okay. Plus, we have minus 0.666 minus 0.666 plus 1 minus 0.666 plus 2 divided by 3 factorial, and here we have 165. Okay, so this is yn, del square yn, and del cube yn, and we have up to del cube only. Okay, so we have 3 differences, so we'll have at the most 4 terms here, and this is equal to, so what we can have is 1001. This term will be minus 0.666 into 658, then this will be minus again, so it is minus 0.666 into 0.334, and this is 380 divided by 10. This term will be again minus. Okay. So what this term will be? This will be minus 0.666, 0.334. This will be 1.334 and 165 divided by 6. So we can get here value y at 8 is equal to
511.96.
it is going to be 511.96. Is there anyone who is getting the value other than this one? Okay, 512.35. think Anshul is getting this value.
So I'm getting 512.348.
512.35. Okay, is there any other value?
Sir, 512.347.
512.347. Okay, so there are the three values now. Some are getting 511.96. Okay, some are getting this 512.35. These two values are nearby same. Okay. Yes. E48. Again, the another values. So 512.348.
Same, sir. 512.348.
Sir, I am getting 511.89.
511.89. So see, if you'll calculate with this accuracy, okay, I think these three values are very close. So 512.35, 512.347, 512.348. Okay, so these values are very close. Okay, so I hope I want you to calculate the values. Okay, yeah, that's correct. Okay. So actually, this value we can consider as 512.35. I'm rounding this off now. This also round off and this also round off. Okay. So this value we accept. Okay. 512.35. Okay. So actually, the value should be nearby 512. Okay. It's going to be 8Q. Okay. So the value should be nearby 8Q. So what do you get 8Q? I hope it's 512. Yes. Okay. So the value should be near about 512. This value is also very close to 512. Okay. But most of you are getting nearby this value. So I'm accepting this. Okay. So this slightly values were at a distance from the polynomial x cube, and that's why we are getting this slight difference. Okay, so you all are correct. Okay, you have calculated the correct value, so there is not any problem. Okay, so you all got the correct value. Yes.
Sir, can you please repeat why we are getting different values?
Yeah. If you look at these values, okay. So if you look at this, it seems to be x cube plus 1. This value is also going to be x cube plus 1. Okay. This value is exactly x cube, and this value is x cube plus 1. So the approximate polynomial is x cube, okay, and plus 1. Okay. So that's why I approximated this to be 8 cube. Got it?
Yes, sir.
Yeah, because see, one point is on the spline. This is a cubical line or cubical spline. So cubical spline, these three values are following x cube plus 1, but one value is away from the x cube plus 1. So that's why we are not getting exactly 512 plus 1. Okay, but we are getting 512 plus something, and that is nothing but this term's average. Got it?
Yes, sir.
Okay, so I said that the value will be nearby x cube. Okay, so here it was easy to identify in this example, but need not necessarily every time you will have a good polynomial. Okay, so all of you got this answer or nearby this. Okay, so 3.5 0.347 is also accepted, 0.348 is also accepted, or 3.3 for something will be also okay. Yeah, so no issues. Okay. So that's why I have converted that 2 by 3 into 0.666, so that you will get, all of you will get the same answer. Okay. So is there any doubt in this example? Is there any doubt in this
No, sir.
example? Okay. So all of you got this one.
Yes, sir.
Okay. So this Newton's forward difference formula and backward difference formula, they are applicable exactly when the data is equally spaced. Okay. So when we consider the data, or we record the data, and this data is basically, okay, either we observe the values or we record this data from the sensors. Yeah, so if you see our first example, that rocket launching, so we do not observe it, we record it from the sensors. Okay, and like that. So this interpolation helps us to find the missing data, or to find the predictions. Okay, so we can see in the last example, I was able to predict the value, that where it will be nearby. So that was a prediction. Okay, or the 25 velocity at 25 seconds, that was a missing value. So it may happen that your sensor goes fail, or the system, we have some system problems, and then we are not able to get the data. So how to get that data? Using interpolation. Yeah, so that was when we are using the equally spaced data. That means we are using we are given a timer to a sensor, and then that is observing the value or recording the value. Okay, so if the data is equally spaced, we go with the Newton's formula. Either it may be forward difference or it may be a backward difference. So basically, if the value that we want to find is nearer to the first value or initial value, then we go with the forward difference formula. Okay, and if the value is closer to the end value, then we go with the backward difference formula. So that's why we can go with the forward difference as well as the backward difference. Okay, what if the data is not equally spaced? Okay, now that is a question. Okay, because so we may not have the data every time very good after equally spaced, but sometimes we may get a random data also. And if we get the random data, then we may not have the data to be equally spaced. And in this case, okay, how to find the missing value, or how to predict the data, or how to predict the next value. So here we have the another formula called Lagrange's interpolation formula. Okay, so the Lagrange's formula is applicable for unequal intervals when the data is not equally spaced. Okay, so let us see what is going to be the formula. So we go for the Lagrange's interpolating polynomial, or we go with the formula. So basically, this is for unequal intervals. So when data is not equally spaced, so we want to find the value of y at any x. Again, so this x we will be given. We want to find the value of this y at x. So what you have here, this is x minus x1, x minus x2. and so on the term x minus xn into y0. This term is divided by x0 minus x1, x0 minus x2, and so on the term x0 minus xn. So try to understand the construction of this term. Okay, we want to find the value at y is equal to x. So we have x minus x1, x minus x2, x minus xn. x0 is not taken in the numerator, but in the denominator we have x0 minus x1. These are not equally spaced values. So the difference between x0 and x1 and x1 and x2 is different. Okay, so next term we have x minus x0, x minus x2, x minus x3, and so on the term x minus xn. Now here we have, this is x1 minus x0, x1 minus x2, x1 minus x3, and so on the term x1 minus xn. And here we have y1. Okay, see the numerator. In the first term, I am not considering x minus x0. And in the denominator, I am replacing x by x0. Now see the next term. I am not considering x minus x1 term in the numerator, and in the denominator, x1, x is replaced by x1. And here you can have y1. Okay, and so on. We can go on constructing all the terms. Okay, so in the first term, we don't have x0 in the numerator. Second term, we don't have x1 in the numerator, and so on. The ith term, okay, will be x minus x0, x minus x1, so on the term x minus xi minus 1, x minus xi plus 1, x minus xi is not there, and so on, x minus xn. The denominator, we have xi minus x0, xi minus x1, and so on the term xi minus 1, xi minus xi plus 1, and so on the term xi minus xn, and this is yi, and so on the term. The last term will be plus, the last term is x minus x0, x minus x1, so on the terms x minus xn minus 1 yn, because this is the nth term we will have. Okay, so here we have xn minus x0, xn minus x1, and so on the term xn minus xn minus 1. So this is the Lagrange's formula. Okay, so try to understand the construction of this. Okay, and now I am going to write the general form. Okay, so I am going to write the general form for this. So what you have here, y at x is equal to, okay, this is the summation. Okay, so it is the summation a running from 0 to n. Okay, and this term we can write the product. Okay,
So we have a lecture at 3:35.
okay. So we can write this as x minus x0, we can write x is going to be x minus, we can have the product is the product and I not equal to j, okay, up to n x minus xi and here we have the product I not equal to j xi minus x. Okay, and here is going to be y.
Excuse me, sir. Can you show the slides once again?
Sir, you are
Sir, you're on
muted.
mute.
We can write that numerator in the form of a product. We can write the denominator in the form of a product, and this sum for all such terms. Okay, so we have to consider summation for all the terms. Okay, so this is the Lagrange's formula. We'll see more examples in the next lecture.
Sir,